This is 2018 AIME I problem number 14, and here is a view of this problem. We are given a heptagon, a polygon with 7 vertices. I only did draw the circle, and I dissected it into 7 vertices. A frog starts at vertex S, so we have our frog here at point S, and at each time we would jump to one of the two neighbors. For instance, if you start at time 0 at S, which we know, at time 1 we can be either on P1 or P5. We have to jump, we cannot stay on S, okay? And if we are at P5, for instance, the following period we will be in P4 or S, and so on. The only exception is the vertex E. If the frog somehow lands to vertex E, which can happen if in the previous step you were in P4 or P3, then the frog remains at vertex E. Okay, so we need to find the number of ways to reach vertex E in no more than 12 steps. Okay. So the approach that I will use for this problem will be pretty much the same as the approach we used for problem number 10 in AIME I of the same year. So that's strange that we have two AIME problems using recursion in a sort of a geometric fashion. But let's just do regardless. So because I spent a lot of time on question number 10 to explain my recursion steps and everything, I will be faster on this one. In fact, I will provide two solutions for this one, both of them recursion, one of them step by step solving it. Second one, we will try to find a closed form formula for that, alongside the official solution, obviously. Okay, so let's try to, like we did in problem number 10, if we want to be in at time t, if you want to be on vertex S, the only way you can be on vertex S at time t, if in the previous time you were in time t minus 1 you were in vertex P5 or you were in vertex P1. These are the two neighboring vertices to S. So at time t you can end up in S only if in the previous time at time t minus 1 you were in P5 or P1, and so on. So therefore I can easily write each of these vertices. So you can end up in P5 at time t if in the previous step you were in P4, or because P4 is a neighbor to P5, or if in the previous step you were in vertex S. And I'll go ahead and continue in that fashion. So you can end up in vertex P4 in the previous step only if you were in P5. You cannot come to P4 from E, because once you land at E, you stay there, right? So you remember, so you stay there, you stop there. So therefore, the only way you can end up in P4 at the end of time t is if in the previous time, at time t minus 1, you were in P5. The same thing will happen for P3, is only when in the previous step you were in P2. For P2, in the previous step you were either in P3 or you were in P1, basically. And finally, if you want to end up in P1 at time t, in the previous step you had to be either in S or at P2, and that's it. So we gave a description. Well, obviously if you want to end up in E at time t, okay, we forgot the main one apparently, then you have to be so you would be in P3 in the previous step, or you would be in P4 in the previous step. And that's it. So now that we have our recursion formulas, all we need to do is progressively solve it to get E. Well, because the question says in no more than 12 jumps, what we need is E, well, in one step, and so on. So, well, you can say E1. Well, in obviously 0th step you can't be, so let's call it E1, E2 plus all the way up to, we need the sum E12. in 12 jumps or less. But notice that this is simply equal to this sum, right? So E1 we can replace it with P3 of 0 plus P4 of 0 and so on. So P3 of 1 plus P4 of 1 and all the way up to P3 of 12, well, the previous one, which is 11, sorry for that, oops. Okay, 11 plus P4 of 11. All right, so we have more or less an idea what we need. Let's go ahead and create a table like we did in problem number 10 and finish this problem. So I will, so probably I will just make it smaller scale so that I don't lose my picture because it gives me a lot of information. So we have, and let me change the color of my marker. So let's go ahead and do that. So probably I will need, why not, green. Awesome. Oops. Okay, good. So that should be green. All right. So what I have is, well, let's first draw our steps. So at step 0, step 1, and so on. Step 2, 3, 4, 5. Well, I will have quite a lot of steps to check, right? So 8, 9, 10, and I will need one more. So let's go ahead and remove that thing here. So probably I will just put it down here. Okay, so therefore it won't, yeah, I no longer need these. Okay, so going back, let's first close these two parentheses like that. We have a plus sign here, and then we have one more row to check, and that would be 11. Obviously I want to stop at 11 because that's all I need, right? So this sum, all I need until time 11. So this is my times, or steps, if you will, number of steps you can call it. And I wonder how many different ways can I end up in vertex P1, P2, and so on, P3. Well, you can put E in the middle, or I will just ignore it. I don't need it, to be honest. P4, P5, and P6. Well, there's no P6, obviously. We have an S, and that's it. So, before I start my calculation, I want to step back and just check something quickly. Because at step 0, I am at point S. So there's so this is a 1 and everything else is basically a 0. Actually, let's change the color one more time. So these are all zeros. So and then check this out. So obviously after one step I can be either in P5 or P1, and that's well, obviously confirmed by this recursion here. So there's really one way to end up here and one way to end up here. But what I want to take so attention is, hey, these are all impossible, right? After one step you can't be at S, right? Then it's kind of interesting to realize that the only way you can end up back in S, for instance, would be in even number of steps. So in odd number of steps, no wonder S would just be 0. So I can just put zeros right here. Does that make sense? The same thing, for instance, P1. I can only end up in P1 at odd numbered steps. So therefore, in even numbered steps, there is no way I can end up in P1. The same thing for P3, right? Does that make sense? And P5. I can only end up in P5 in odd numbered steps, right? So these are all zeros. And P2 and P4 quickly. So P2 I can only end up in even numbered steps. So therefore odd numbered steps will be 0. And the same thing for P4. I can only end up in even numbered steps, 1, 2 steps at the least, right? So odd numbered steps, 0 here. That significantly reduces the work, computational work. I need to just calculate a significantly less number of points. And finally, just to remind you, all we need is this sum right here, and this sum is just the sum of the two columns here. P3 and P4. So therefore all I care is the sum of these two entries here. So I can put a summation sign. I need to sum all the P3s and all the P4s. That's it. Okay, so if everybody is ready, we can begin starting the recursion. For instance, S here, we can get to S if in the previous step we were in the previous step means the previous row. So because I want to calculate this, if I was in P5 or P1, P5 is 1, P1 is 1, so this is a 2. P4, I can end up in P4 if in the previous step I was in P5, so which is just a 1. So this 1 I carry it over here. And I can end up in P2 if in the previous step I was in P3 or P1, so 1 plus 0 is just a 1. Does that make sense? Okay, next step, step 3, P1. So P1, I can end up in P1 if in the previous step I was in S or P2. So therefore S and P2 is 1 plus 2 is 3. P3 is just P2, which is just 1. And P5 is P4 plus S, which is 3. We continue. P2 is just P1 plus P3 in the previous step, which is 3 plus 1 is 4. P4 is just P5. We established it in the previous step, so 3. And S is just P5 plus P1 from the previous one. P5 plus P1 is just a 6. Okay, so P1 is just the sum of S, 6 and 4, so which is 10. This one, P3, will be just P2 from the previous step, and this one is just a 9. I hope that's clear, right? So it's just, so for instance, P2 in step 6 is just P1 in step 5 plus P3 in step 5, which is just 14. And this one, P4, is just, in step 6 is just P5 in step 5, which is just a 9. And this one is 19. So I can continue 14 plus, so that's a 33. This one is a 14, and this one is a 28. 33 plus 14 is 47. P4 is just P5, right? So P4 is just P5 from the previous step, so that's a 28. And this one is 28 plus 33 is just a 61. This one, P1 in step 9 is just S in step 8 plus P2 in step 8. S in step 8 is 61. P2 in step 8 is 47. 61 plus 47 is 108. P3 is just 47. And this one is 89. My bad. 89. Almost there. P2 now is 108 plus 47 is 155. P4 comes from the previous guy, 89, and 89 plus 108 is 100 plus 97, so it is 100 plus 97 is 190, hold on, that is correct, 197, and almost there, so 155 plus 197 is 152 plus 200, so it is 352, 155 here, and finally this one is 286. That's it. So we completed our table. Now all we need is to sum the P3s here and then the P4s and add those numbers up, right? So we have 1 plus 4 is 5, 19, 66 plus 155 is 1, 2, I believe, 221. In a similar way, we can add the P4 column, 1, 4, 13, 41, 130 here. And if I add these numbers, these numbers would give me the final total sum would be 351, I believe, is the answer. Now I want to mention a few things about how to solve this problem with a recursion rather than doing all this calculation. This calculation is nice and it was helpful for both of these questions. However, at the end of the day, what if the question didn't say less than or equal to 12 steps? What if the question said less than or equal to, say, 25 steps? The table would be significantly longer and there's a significantly higher chance that you will end up messing up the calculation, right? So for that reason, you can follow up the official solution, which basically is pretty cool. It tells you that if you want to end up in vertex E in any given step, in the previous step you need to be in one of the one of these two, these two vertices. And if you want to end up in one of these two vertices, you have to be in one of these two vertices in the and then if you want to be in one of P2 or P5 in the previous step, so you are either on this set or on this set. So let's label these sets as A, B, and C. So let's write this carefully, and hopefully that would lead us to the result. So if you want to end up in C, the only way you can end up in C is if in the previous step you were in B. If you want to end up in B, you had to be either in A or C in the previous step. And finally, if you want to end up in A in the previous step, well, this one's curious. You had to be either in A, because for instance you were in S and you can go to P1, so you can remain within A, or you had to be in B. Now that can help us establish the counting argument. So we can just label, we can just name the number of paths of after T steps, like we did in let's just so let's say that so in this case, so we can end up in C in, let's say, T steps only after if in the previous step, in step T minus 1, we were in B. So therefore CT is just B sub T minus 1. Does that make sense? And in a similar way, in step T you can end up in B if only if in the previous step you were in, so the number of steps to A that ends up in A in the previous step plus the number of steps that end up in C in the previous step. If you add these two, will give us the number of steps that you can end up in B in step. So therefore little a, little b, and little c is number of ways you can end up in these three sets A, B, and C, as you can see in the picture, in the given time frame, right? So, or number of steps, if you will. And at step T, you can end up in set A only if in the previous step you were in A, so this is T1, or in the previous step you were in B, and that's it. Well, obviously you need to also check some initial conditions, which we already did, right? So for instance, okay, let's first decide how to solve it. For instance, we can decide to solve it for C, right? So why do we want to solve it for C? Because obviously the number of ways you can end up, so there's an invisible recursion here. The number of ways to end up in E at the end of step T is just only if previously you were in C, right? So therefore that's why, right? So all I need is to figure how many different ways I can end up in C, in the set C in the previous step. So in our case, we need to find E12, so therefore, which is equal to C11. That's all we need. We need to calculate C11, yes. Right. Okay, so let's just go ahead and do that. So this is exactly 12 steps. Sorry, I'm high. So the 11 is just C10. We need to find all of them, right? Because it says less than. So C9 and so on. So therefore E2 is equal to C1. Well, obviously these are 0, but I will write it regardless if so anyhow. So I need to find the sum of all these numbers, so which is the sum of these numbers. Okay, let's go ahead and solve this system of equations for C, right? So for that reason, I can just eliminate the B from the equations first. So let's eliminate B by substituting the B expression in this one and this one and replacing it with a C type of expression. So therefore the second expression becomes, so this one, the BT is the same as C sub T plus 1, right? So therefore this is C sub T plus 1 is equal to A sub T minus 1 plus C sub T minus 1. So that's what happened here. And for the third equation, we still have AT is equal to A sub T minus 1 plus B sub T minus 1 is just CT. We know that. And finally, and we can replace, so here, from here we realize that A sub T minus 1 is simply equal to C sub T plus 1 minus C sub T minus 1, and I can substitute now the A into this second expression. So okay, so let's do it. So A sub T is just one shifted to these guys, so therefore this is C sub T plus 2 minus C sub T is equal to a sub t minus 1 is the same, c sub t plus 1 minus c sub t minus 1, and finally we have c sub t here. Oh boy. Let's just put the c sub t just underneath, plus c sub t. Okay, and that's it. So now we have a recursion. Well, obviously we can do better than that. Yeah, so c sub t plus 2 is simply equal to, let's move things to the other side, c sub t plus 1 plus 2 times c sub t minus c sub t minus 1. Well, obviously this is not very handsome, so let me just write it as c sub t plus 1 is equal to, so let's shift it, c sub t plus 2 times c sub t minus 1 minus c sub t minus 2. Okay, now this is handsome. Okay, so therefore we have already established what we need. So we need c sub 11 and so on. So to get, for instance, c sub 11, I will need to calculate all the way up to c sub, so replace t equals 10, right? So, but to begin using this recursion, I need to calculate, for instance, c sub 0, c sub 1, c sub 2. So after one step, how many different ways can I end up in either P4 or P0, P3 after no step? Obviously, there's no way this can happen. This is 0. How about C1? After one step, can I ever end up in this cell? No way again. That's impossible. But after 2 steps, it is possible. 1, 2. Do you see that? So that there's one way you can do that. And that's it. The rest will be taken care of by the by this recursion, right? So let's go ahead and implement it. So C3 is just, I'll just write it once and then you can take care of it, the rest on your own. So that's just C2 was just 1 plus 2 times 0 minus 0, which is just 1. And now I have an idea. So C4 is just the previous guy, which is 1, plus 2 times the one before that, which is 1, minus the one before that. So that's a 3, and so on. So let me go ahead and write it here. So C5 is just 3 plus 2 times 1 minus 1, which is 4. C6 is 4 plus 2 times 3 minus 1, which is 10, 9. C7 is 9 plus 2 times 4 minus 3, so 8, 5, 14. C8 is 14 plus 2 times 9 minus 4. So we have 18, 32, 28. C9 is 28 plus 2 times 14 minus 9, which is 28 minus 9 is 19, 47. C10, and that's the last one I needed. Oh, sorry, I still need C11 too. Sorry for that. Okay, so that's 47 plus 2 times 28 minus 14, which is just 56 here, minus 14 is 42, so this is an 89. And C11, these numbers are no surprise, right? We got these numbers earlier in the table, right? So if you check, inspect our table, you would see these numbers 9, 14, 28, 47, 89, and 155. So I won't be surprised if the next guy is a 155. 89 plus 2 times 47 minus 28, which is 2 times 47 is 94, plus 93 plus 90, let's say, which is 183, minus 30 is 153, 155. Yes. Whew, so finally I need to add all these numbers. So final answer, so the sum would be 0 plus 0 plus 1 plus 1 plus 3 plus 4, 9, 14, 28, 47, let's shift it a little bit, 89, and then 155. And no surprise, if you add all these numbers, you will get the outcome, the final result of 351 as the answer to this second recursion problem in the same AIME.